Alright, so this is section 5.6 in our textbooks, the kinetic molecular theory of gases. It can be abbreviated the KMT of gases. You'll see me do that quite often. So throughout this chapter we've been talking a lot about the word laws. We've talked about Boyle's law and Charles' law, Gay-Lussac and Avogadro's laws. And let's remember what a law is. A law is a summary of observable behavior. So for instance, we know that for a gas, as the pressure increases, its volume will decrease. That's a law. We've also known that if we combine all of these gas laws that we've talked about, we can form what we've called the ideal gas law. Now, laws might define or summarize observed behavior, but they don't exactly tell us why that behavior occurs. So yes, the pressure goes up, volume goes down. But why does that occur? The why of a law is where a theory comes in. Now, theories aren't just willy-nilly guesses. They have a lot of evidentiary support. There's a lot of backing, a lot of scientific backing. So theories are pretty good. And they give us nice models to try to explain why certain things happen. So here comes the kinetic molecular theory of gases. Okay? The kinetic molecular theory is going to try to help us explain why gases do the things they do. Why do they compress when their volume decreases? Why does the volume decrease when they compress? And why do they increase in volume when the temperature is increased? So there's really four main postulates to this particular theory. And here's postulate number one. The particles of molecules in the gas phase are so small. The particles are so small compared with the distances between them that the volume of the individual particles can be assumed to be negligible. So we think of like in a liquid. We got liquid nitrogen here on the left side. The particles are closely compacted together. So if we fit any more particles inside of the liquid, that has the same effect as increasing the volume of our substance. For a gas, on the other hand, the molecules are so far apart that if we would go ahead and put a couple more molecules in, those couple more molecules could easily fill the spaces that are voided inside of the gas. So we wouldn't increase the volume at all. So for our purposes, for the kinetic molecular theory, we're going to say the volume of the molecules is essentially zero. Now, do we know that to be completely true? No. But it does help us with most of the mathematical processes that allow us to determine certain effects with gases. All right, so step number two of the theory. These particles that make up the gases are in constant motion. They're always moving. And the collisions of the particles with the walls of their container are the cause of the pressure exerted by the gas. So we never essentially think about particles being standing still. That would be the definition of zero, or absolute zero, 0 Kelvin. But we can't theoretically reach that point, so we say that the molecules are in constant motion. And the more molecules we have in motion, the more exertions on the walls of the container, the higher the pressure. Also, the faster those molecules are moving, the more collisions with the container, so again, the higher the pressure. Here's the third postulate. The particles are assumed to exert no forces on one another. So essentially, they don't even know each other exist. They don't run into each other. They don't affect each other at all. They're kind of independent in nature. So they're assumed to not only not run into each other, but they don't even attract each other or repel each other. Now, I think as you're sitting here thinking about this, you could probably say, well, it's probably not always true. Well, you're right. But again, these are occurrences that allow the model to work for most of the time. There are instances where it does fall apart, but it's pretty good most of the time. Lastly, and maybe the most important part of the postulate, or of the theory, is postulate number 4, and that's that the average kinetic energy of a collection of gas is assumed to be directly proportional to the Kelvin temperature of the gas. In essence, if we increase the kinetic energy of a particle, we are then going to increase the Kelvin temperature of the sample, or of that particular sample. Remember what kinetic energy is, if you can remember this from physical science class or from a physics class. It's equal to 1/2 the mass of the object times the velocity of the object squared. Okay? So if we increase the mass of the object, and it runs the same speed as a different object, it has more kinetic energy, and thus it will increase the temperature. Also, if we'd increase the volume, or not the volume, but the velocity of a sample of gases, that in turn is going to directly affect the Kelvin temperature, so the temperature of the substance is going up. We can see that kinetic energy is directly related to both mass and to velocity. Okay, so those are our four postulates of the kinetic molecular theory. When you understand those four postulates, if we kind of keep those in mind, we can think of our gases as being something called ideal gases. So ideal gases follow the postulates represented above. And for most of the things that you're ever going to work with in chemistry, these postulates hold true. And you can think about all gases as being ideal gases. So then you can use something called the ideal gas law. But there are times where the ideal gas law breaks down. We'll get to that in a future chapter, or in a future section, rather, of this particular chapter. Okay, so we won't worry about that now. All right. Let's do a little concept check here. Let's say you've got a sample of nitrogen in a container fitted with a piston that maintains a pressure of 6 atmospheres initially. Initially, the gas is at 45 degrees Celsius in a volume of 6 liters. Now, you cool the sample. What do you think is going to happen to that gas? Let me give you some options. Will the pressure of the gas increase? Will the volume of the gas increase? Will the pressure of the gas decrease, the volume of the gas decrease, or both volume and pressure change? Okay, which one do you think is going to be the case? Well, hopefully you selected this one. Let it be. The volume of the gas is going to decrease. Okay? Remember what we said about the pressure. We said that the piston maintains a pressure of